Our next presenter is Dr. Zhang from the New York University. Thank you very much for coming, Yu.
I thought to be effective, I put the New York University photo on the title slide. So this is our main campus in Washington Square when we have graduation ceremony here. You can see this pretty nice bird eye view here. And the topic I'm going to discuss is engineering dental ceramics for damage resistance. We all know that compared to metal-based restorative materials, and ceramics, they have improved aesthetics and about compatibilities. However, ceramic materials are brittle, susceptible to fracture. Therefore, some of the ceramic restoration systems experience high failure rates. Now, Susan Shearer and George Quinn and Jenny Quinn, those clinical studies on clinically failed crowns showed there are a variety of fracture modes. Right? Crack can initiate at the contact surface, the occlusal surface, and then propagating down, resulting in chipping or fracture of the restorations. And the cracks can also form at the cementation integral surface, resulting in what Bob Kelly refers to the bulk fracture of the restorations. And for some glass ceramics, we even see that crack can form at the margins, resulting in semi-lunar fracture, so-called lunar fracture here. But if we take a closer look at those complex systems, really, the occlusal contact fracture really is determined by the sliding contact resistance of the ceramic restorations. While the cementation internal surface fracture and the margin fractures, they are determined by the fracture damage resistance. In other words, the strength of the materials. So from the rest of my presentation, I'm going to focus on the material performance in terms of contact and fracture damage resistance. I think you can, by talking both, you can prevent all sorts of damage fracture modes. So let's begin with the contact damage. And to talk about contact damage, we really need to start with occlusions. And occlusion really can be described as a cusp tip in contact with the inner incline and sliding down towards the central fossa and the lifting off. This kind of cyclic loading effect. So there is involving a contact slide lift off, this fatigue behavior. Now, if you would take a closer look at this system and you see the radius of the inner incline is on the order of several centimeters, about 10 centimeters. And the radius of the cusp, the young cusps, is on the order of millimeters. So it's in the inclines almost 10 times greater than the cusps. So based on that, we can simplify now the systems to see that sliding contact almost can be simulated by a zirconia. Remember, I was talking that previous slide, and due to the fracture damage resistance, the strength of the material. So the cementation internal surface crack is mainly governed by the strength of the material. You have a zirconia much stronger than alumina, the crack is not easily to pop up in these systems. In the case of alumina lithium disilicate material, you have relatively lower strength, and then you're also vulnerable to fracture damage. So what we did was we put alumina, veneered alumina subject to cyclic fatigue, 200 Newton. And about 85,000 cycles, Christian Stepp's data showed that about 90% of materials develop the cementation integral surface bulk fracture. And if you do the same load onto the zirconia system, that's about 500,000 cycles, and you don't have any cementation radial bulk fracture, what you see is contact area crack and start to propagate down, reaches the near core interface. And that's why we think, because zirconia is not susceptible to contact the flexural damage, therefore the giving enough time for the occlusal surface to result chipping. And interestingly, clinical studies showed that the alumina and the zirconia have very similar failure rates, but the only difference is alumina is more attributed to bulk fracture, while zirconia has more veneer chipping. And it really, in fact, the clinical study did show, I don't know why the slide's playing up, and did show that for relatively weak materials like alumina and the lithium disilicate, flexural damage dominance. You have bulk fracture in the single crowns and connector failures in multi-unit bridges. All right, so that's where the flexural damage plays a role. In the case of zirconia, whether you're single crown or multi-unit bridges, mainly resulting from veneer chipping and the fractures. So this is the problems that we're facing in the current all ceramic restorative materials. And in fact, it's sort of motivated by those problems, as Professor Kelly mentioned. Now there is a trend in US to develop this monolithic zirconia. There's no veneer anymore, just one single body layer zirconia. But the concerns now, you have, Thomas has mentioned, you have hydrothermal degradation concerns, and you have wear of the opposite dentition concern. So we propose now to address those issues to develop a functionally graded materials. So what we're trying to do is now we have a zirconia material, and then we infiltrate it with a aesthetic glass from top and the bottom surface. But that's optional. You can only infiltrate on the occlusal surface, or you can just choose to infiltrate on the cementation internal surface, or we can combine our techniques to infiltrate occlusal surface and the aluminum oxide in the cementation internal surface. All those options we can play. But here I'm just going to show you an example that we infiltrate both top and the bottom surface. This one's very sensitive. If I hold it a second longer, advance number of slides, Jason, you've got to be a little careful with this. And so what we see is now, after glass infiltration, you see that there is a thin external glass layer somewhere between 20 to 50 micron thick on the both surfaces, and then followed by a glass zirconia two-phase materials. And they gradually evolve into a pure polycrystalline materials. And if you do cross-section from surface in, from residual glass to graded structure to all the way to zirconia interior, you do the nano indentation, what we see is the hardness and the elastic modulus increases dramatically, follow a power law relation evolving from surface to interior. So the first test we do is, remember we were talking about two things: the contact damage resistance, the flexural damage resistance. Now let's put this material into the test. The flexural damage, the strength of that material against the zirconia. And then we will show you the material, the contact damage resistance against monolithic zirconia. Not only you have porcelain on it, even without porcelain, we're still confident to match it up. So first we do 3-point banding test. We have a graded structure versus non-graded structure. We see that if you do follow ASTM standards, the 3-point banding test, our material is about 20 to 30% stronger. And then we do more relevant to our dental setup. So what we do is now we have those graded plates bound onto soft substrate load on the top. Now see this, you have support of the denting and the load on top. See how strong those material is. And now we're looking at the cementation internal surface radial fractures. So what we did was we prepared the materials, graded zirconia and a non-graded zirconia as blue. Graded is orange here. And we come up with different thicknesses because some people may suggest that maybe we can have conservative, ultra-conservative approach. We have very thin restorations on the top, and we can have thick ones, 1 millimeter thick. So what we did was we're making materials with different thicknesses. We break as the fashion I showed you before in that way. Just single cycle loading, see the strength. And we can see that load to fracture, the graded is way above ungraded in all thicknesses. Now this is not only true for zirconia. We can also infiltrate alumina with glass, and you will see the same thing. Now we have graded glass infiltrated alumina versus monolithic alumina. You also see the same thing. It's graded and ungraded for the thicknesses we tested here. Now, we also went one step further. We did cyclic fatigue strengths of those materials. Single cycle strengths, yes, I'm convinced it's stronger than zirconia. What about we do the cyclic fatigue test? So what we do is we load them up, a graded plate on composite dental materials subject to a off-axis cyclic fatigue simulating this inclination angle. And what we see is loading on the surface in water. We soak the whole thing in water and see what happens. It's looking at the cementation internal surface fracture. So that's what we see. Here is the number of cycles to failure. And here is the applied load. So for a given load, what we do is we say, let's aim for a maximum load of 600 Newton here. Set up cyclic fatigue 600 Newton, the maximum load. And you sit there and wait until the sample fractures. We have an optical microscope look at this until it fractures. So that's what we see now. For 600 Newton load, for the graded structures, maybe it takes a few cycles. For the ungraded structures, you only need 500 Newton. One cycle you will fracture. So it's a lot stronger. And here I want you to pay attention that the thickness of this plate I use is relatively thin because zirconia is quite strong. If you use about 1.5 millimeter thick zirconia, you have loaded up to thousands Newton to fracture them. So I sort of shortcut and back off a little bit, make a thin material. So looking at somewhere about 500 Newton, ungraded material lasts a few hundred cycles, graded material lasts tens of thousands of cycles, about 2 orders of magnitude stronger. And this is the same thing, it also holds true. And when you do graded alumina versus ungraded graded alumina, in this case you can do about 1.5 millimeter thick alumina plate on Z100 support, and then what we see is now 700 Newton ungraded material will fracture, and for the graded 700 Newton lasts over 1 million cycles. And the little arrows here is representing a run out. We run up to about 1 million, 2 million cycles. It doesn't fracture, we call it off because it's taking too long. So it's a run out. So the first thing come up to us is, why does surface gradients stronger than ungraded materials? Is that because we graded the surface, you introduce the residual stresses, make the material a bit tougher on the surface? A simple test, the Vickers test on the graded and ungraded surface, we see the crack lengths are very similar. I'm not showing you here trying to use Vickers indentation method to measure the fracture toughness. You all, by now, you all read George Quinn's paper. So, but here I'm trying to demonstrate is you indent on a surface, how long the crack you can generate, give you a relative reference and how tough the material is.